Welcome class to our first video notes from Unit 1B, and they are on Skill 1. And you will get your Unit 1B pretest when I see you next, but you can know right now that our first skill will be on graphing inequalities and systems of linear inequalities. So this is something that was covered in Algebra 1, but we do feel the need to repeat it here in Algebra 2 just to make sure we're all on the same page moving forward. So just a couple of things to remember is that first you just graph the line, like what the equation would look like if it had an equal sign as opposed to one of these inequalities here, these greater than or less than or equal to signs. So you just graph the line as is. And then from there you decide whether or not you need to use these dashes right here. And that's what you use if the symbol only has greater than or less than sign. Or if you go ahead and keep it as a solid line, and then that's what you do when you have greater than or equal to or less than or equal to signs. But after you have dotted in your line or graphed your line, you then need to decide where to shade. And I'll talk a little bit in a moment about why we shade. But basically, linear inequalities have infinitely many solutions because the solutions are not just where y equals mx plus b, but they are also where y is greater than or less than mx plus b, and then by the way, if your equation is in slope-intercept form, as these are written here, then you can just follow the direction of the inequality to know whether or not you shade above the line or below the line. So if, and this is a big if your equation is in slope-intercept form, then greater than symbols mean you shade above, but less than symbols mean you shade below. Now, if your equation is not in slope-intercept form, then what you would need to do is pick a point. And it's important that you recognize it has to be a point that's not actually on the line. Otherwise, it's not going to tell you whether or not you need to shade above or below. You pick a point that's not on the line, you plug it into the inequality. Okay, you plug in both the x and y coordinate. It's important that we understand that too. You plug in the whole point, both the x and y coordinate, into the inequality. If it makes the inequality true, that means that it is one of the infinitely many solutions, and therefore you just shade the side that that point is on. And then if the inequality is not true, that means it's not one of the infinitely many solutions, and so you would want to shade the opposite side, not the side that point is on. The opposite side would be the side that has all of the solutions. Okay, so this is what you do for one line, and then if you have more than one line, you just repeat steps 1 through 3 for as many lines as you have. And then what you would do is look to see where the shading overlaps. If you have more than one line, look to see where the shading overlaps. So I hope that as you're watching this video, you're kind of highlighting the same things as me, underlining the same things as me, adding in all these notes because they help when you have to go back and review them later. Okay, but now I'm going to move on to our set of examples and then also kind of explain why we shade. And that is because in a linear inequality, there are going to be infinitely many solutions because not only do you include the points on the line or the 2 lines or the 3 lines or the points they have in common, but also all of the points that were shaded. That are shaded, and then we consider shaded twice if you had to shade for 2 different lines. All the points that are shaded twice are considered solutions to the system because they'd make both inequalities true, which is what this says right here. And so the reason we shade is because we're trying to show all of the solutions, right? And there's infinitely many of them, so it's impossible to actually put a dot on every single solution. So instead we shade to show this is the area where the solutions would be. But that's what the shading represents, is where all the solutions are. It's like the pool of solutions. So let's try a few examples and then you can kind of see how this works. So with example 1, we have a system of inequalities. Okay, so this here is a system because there is more than one. Okay, so when you have more than one, that's considered a system. So that's where you have to actually graph both lines and then find where the shading happens twice, and that is indicating all of your solutions. Okay, that where the area that has been shaded by both inequalities. Okay, so what I notice with this first inequality is that it has a greater than or equal to symbol, which means I'm going to use a solid line when I plot it. But the line that I plot is just as if it were the same equation but with an equal sign. So the line is representing where y is equal to negative 2/3 x minus 2. And that one's in slope-intercept form, which is nice. I just go plot my y-intercept at negative 2 and then my slope of negative 2/3. And I like to do my slope a little bit backwards as well, just to be able to get a good line going. Okay, so that's my solid line. Now the shading for this line is going to happen above the line. Because there's a greater than symbol. So I'm going to shade in this general area. Right now I'm just kind of showing the general area because I'm going to wait and see where the shading would happen twice before I actually shade it all in. But I've got inequality number 1 done. Okay, so now I'm going to look at inequality number 2, which I see has a less than sign. So then that one is going to be a dotted line because it doesn't have an equal sign. And this equation is in standard form. So first of all, I just graphed the equation for the line where x minus y actually equals 6. Not less than 6, but equals 6. I graphed that line. And I'm going to go ahead and use x and y intercepts. So I can see that the x-intercept for this line would be 6. And the y-intercept for this line would be negative 6. So really quick review of how I do that. To find the x-intercept, I just plug in 0 for y, and then that just left me with the equation x equals 6. And then to find the y-intercept, I plug in 0 for x. So that left me with this equation, negative y equals 6, and then you just have to divide by negative 1 to find out that y is negative 6. So just a quick review of intercepts. So I'm going to plot a point at 6, 0. 1, 2, 3, 4, 5, 6, and then a point at 0, negative 6. And then I'm going to use a dotted line to connect those points because it's not a solid one. It's a dotted one because the inequality was just less than. And then I'm going to pick a point that is not on this line. I think I'll pick the point 0, 0 to test with the inequality. So I'm going to test the point 0, 0 by plugging both 0 in for x and y. So I'm testing the ordered pair 0, 0 because it's clearly not on the line, and I'm just checking to see if this area of the line would be a solution. So I plug in 0 minus 0 and I get 0, and that is less than 6. Check. 0 minus 0 is less than 6. That's a check. So that means that this is the side the solutions would be on. This is the side where I would shade for the second line. And then now it becomes really obvious to me where all of my solutions are. So the part that would be shaded twice, so to speak, is right in here. It's the part that stays above both of the lines. This part that I'm shading in green would be considered my area. The area or the pool upon which I can grab all of the infinitely many solutions. They would all be somewhere in here. So for an example, because I have to list 3 sample solutions, so maybe I'll just pick one out. So let's say I pick this point right up here. That would be 1, 2, 3, 4, 5, 6, 7, 8 spots on the y-axis, so that would be the point 0, 8. That is one of my infinitely many solutions, all in this green shaded area. I could maybe pick something like right here, nice and easy to see, where x is 2 and y is 2, because it's 2 units to the right and 2 units up. Also nicely there in my shaded area. Maybe I'll pick something over here on the negative side, which looks like it's 2 units left and 3 units up. So these here are 3 solutions that all end up in this area, and you can see there's infinitely many more that I didn't pick. And actually I could have used 0, 0 as well, because I tested that one and it worked. So that was example 1. And we'll do a similar thing for example 2. Okay, so here we are in example 2, and we have again 2 different linear equations here. The first one has a less than symbol, which means I'm going to draw, or when I graph the line, I'm going to make it dotted because the inequality was less than. So I graph the line as if it were just y equals negative 3x plus 1, but y is actually not going to equal negative 3x plus 1, it'll be less than. So I have to be careful and simply dot in the line. It just acts as like a boundary, not as an actual part of the solution set. And if you color a line in, that means you're including it as part of the solution set. But this is not part of the solution set. This is just a boundary for it. Okay, so this has a y-intercept of 1 and a slope of negative 3. And when I connect these, I will do so with a dotted line, because what I really want to show is where y is less than negative 3x plus 1, which would be values where the points are what we call below the line, where the y values would be less than these numbers here, negative 3x plus 1. And again, when your equation is already in slope-intercept form like this one, then you can just look at the direction of the inequality. When it's less than, you shade below. Now, the second one, or the second line, I should say, is in point-slope form. So, and I recognize that the inequality is inclusive. It has an equal sign. That means I'm going to draw a solid line. That means that the line itself is part of the solution set. And I'm going to graph the equation for the line as if there were an equal sign. And this is in point-slope form, so I can know, because of the form it's in, that one point on the line would be negative 5 for x and negative 3 for y. So I'll plot that point. 1, 2, 3, 4, 5, 1, 2, 3. Negative 5 for x. Oops, I messed up. Let me just get that out of there. Okay. So I'm going to do negative 5 for x, 1, 2, 3, 4, 5, negative 3 for y, 1, 2, 3. So start there, and then I can see that my slope from there is 2. So I go up 2 over 1, up 2 over 1 from that point. Okay, and I'll make this one a solid line. Now, even though this line is not in slope-intercept form, the y-coordinate is almost isolated. In fact, maybe I'll write it as if the y-coordinate was isolated. So as long as y is alone, you can follow the direction of the inequality to decide where to shade. And so I isolated y, I got y alone, and it's showing me that y is going to be greater than or equal to the rest of the line. So I'm going to want to shade above the line. And when I do that, then my solution set becomes more obvious. It would be anywhere below the red dotted line but above the blue solid line, and I can include points along the blue solid line that are also below the red dotted one. So I can include everything in here and along the line itself down here because it's solid, so it includes everything on there. So when I'm picking sample solutions, right, because there's infinitely many of them, when I'm picking sample ones, I want to pick something in the area that had been shaded twice. Something obviously in the area, like maybe right here. It's very much into the deep into the shaded area. So it looks like that's an x value of 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 3. So I could say negative 9, 3 would make both inequalities true. I could do maybe something over here. Looks like that would be at negative 4, positive 4 for x and y. And then maybe I'll just pick something way down here on the x-axis, negative 10, comma 0. Just, that was a nice obvious one. But anything in that green area could work as a solution, and maybe we'll show what I mean by that. So a solution would be something that makes both inequalities true. So maybe I'll check the negative 4, 4 one, just to see how that works. So if that's a solution, that means I should be able to plug 4 in for y and negative 4 in for x into each inequality and end up with a true statement. So I'm plugging it into this first one right here. I plugged in negative 4 in for x, and then I plugged in positive 4 for y. And when I did that, I get that 4 is less than 13, which is true. So that was definitely a solution for the first line. And then I would also check it with the second line. So again, I'm plugging in 4 for the y, so I get 4 plus 3 is greater than or equal to 2 times, and then I plug in negative 4 for x. And that tells me that 7 is greater than or equal to 2 times 1, which is 2, which is true. So that's what it means for something to be a solution, is that when you plug in both of the coordinates in for x and y into both inequalities, it would make both of them true at the same time. That's what all these green points are doing over here. Any point in this green area is going to satisfy both of these inequalities. Okay, lastly, we're going to look at example 3, which now you may notice has 3 different inequalities. I've got the y less than 7, the x greater than or equal to negative 3, and the 10x plus 5y greater than 30. So this has 1, 2, 3 lines, and that's okay. In fact, systems can have 4, 5, 6, 7, 8, it doesn't matter. System just means more than 1. And so some of our systems will have more than 2 as well. Okay, so for the first line, I noticed that it's got a less than symbol, which means I'm going to dot in the line. It'll be a dotted line. And it will be the line y equals 7. So I'll graph that line, but I'll dot it in because that's a less than symbol, and then I will shade below. Because the y is by itself, so I can follow the direction of the inequality. So this is going to be a horizontal line because it's a y equals line. We reviewed that back in Unit 1A. So I'm going to go up to 7 on the y-axis. And then basically you just have a horizontal line through the y value of 7, and I dot it in. And then I would shade everything below that line, which if you think about it makes sense because every single y coordinate of these points here would be less than 7. So it works that for the inequality that says y is less than 7. Now for the x inequality, that's going to be a solid line because of the fact that there's an equal sign under the greater than symbol. And the line that I'd be graphing would be vertical because it's an x equals line. So I go to negative 3 on the x-axis. I'm going to draw a solid line through the x value of negative 3. And then I'm going to shade everything to the right of that value because I want to shade values that are greater than, more than negative 3, which for x would be located on the right-hand side of the x-axis, right? These are all x values that are more than, greater than negative 3, so I would be shading to the right. Okay, then my last inequality is in standard form and it has a greater than sign. So that means I'm going to graph a dotted line that has the equation 10x plus 5y equals 30. And this equation is set up nicely again to use x and y intercepts. So again, x-intercept is when you plug in 0 for y, which would leave me with this equation, 10x equals 30. So then x will be 3. So my x-intercept is 3, 0. And then my y-intercept is what I'd get if I plug in 0 for x. So that would leave me with 5y equals 30, which would tell me that y should be 6. And so that y-intercept will be 0, 6. So I will plot those 2 points, 3 for x, 6 for y. I'll connect them with a dotted line because I only want points that are greater than, points where 10 times x plus 5 times y is greater than 30. So to decide whether to shade up here or down here requires me to pick a point that's not on the line. So I'm going to pick 0, 0. That's the easiest point to pick if it's an option because it's really easy to plug in zeros. And I'm going to test the point 0, 0 with this inequality to see if it's a solution or not. That means I plug in 0 for x and y, and I check to see if that is greater than 30, but it's definitely not. That is definitely not a solution. 0 is not greater than 30, which means that this area right here where 0, 0 is not part of the solution set for this green dotted line. So actually I would need to shade on the other side. Okay, so my solutions, the places that was shaded 3 times, would be anything below the horizontal line, to the right of the vertical line, and above this other dotted line here. Would be all of these points that are in this area. Sort of this area over here would be where all of our solutions to this system of 3 equations is. So I could pick, let's see, it's kind of going to be hard to see, but I could pick, say, right there, where x is 1, 2, 3, 4, 5, 6, 7, and y is 3 as a sample solution, 7, 3. I could maybe pick the one above it as well, 7, 4, right? Because that would also be in there. Maybe I could pick something sort of way down here, or maybe way down the x-axis, like over here somewhere, because all of that would be part of my shaded area. And so like maybe I could say something like positive 12 or 15 or something for the x-axis. I'll do 15, make it go really far down. Yeah, so anyways, these are sample solutions for this system of inequalities. And we could check again just to make sure. Maybe I'll check the 7, 4. So that means I should be able to plug in 7 for x and 4 for y into all 3 and then make this equation true. So maybe we'll check the first inequality, which only has a y. So is 4 less than 7? Yes, it is. Then we can check the second inequality, which only has x. Is 7 greater than or equal to negative 3? Yes, it is. And then we can check the third inequality. I have 10 times 7 plus 5 times 4. Is that greater than or equal to 30? Yeah. 70 plus 20. Yeah, that's definitely greater than or equal to 30. So 7, 4 fulfills all 3 inequalities, and that's what makes it a solution to this system of inequalities, is it makes all 3 of them true at the same time. Okay, so now what I'd like you to do right now in class is to try these 2. Turn the video back on so that you can check your answers. Okay, welcome back. So these are the solutions that I have for you try A and B. For you try A, you should have a dotted line at y equals 5, and also a dotted line with a y-intercept of -1 and a slope of 2. For the horizontal line, you would shade below it for y values that are less than 5. For the slanted line, you would shade above it. So the area in green here is the place that's both below the horizontal line and above the slanted line at the same time. And I just picked 3 points that were within that shaded area as sample solutions. So the answers for the sample solutions may vary. I just checked to see that they're inside that shaded area, or the area that was shaded twice. For B, you have 3 different equations. The first 2 are slanted. The first one is solid, and that one had an x-intercept of 2 and a y-intercept of -3. The second one is dotted, and they both had x and y-intercepts of -1. And the last one's horizontal down here at -4 and shade above. So this one ended up being just a super tiny little triangular area that was both, or at the same time it was less than or below the red line and the blue line. So it had to be below both lines and above the horizontal line. So it just made this little triangle. So there wasn't a lot of variety in my sample solutions. I picked the x-intercept of the red line because you can include points that are on the line because it's equals. So I included the y-intercept of that line because I could clearly see it was in the area. And then I picked stuff around it. So I saw that I could scoot over 1 at -3 and it was still in there. And then if I just go half distance from x-axis and down 3, I'll be in that teeny triangular area. So those are the points that I chose for my sample solutions. So there is a homework worksheet, and I will be back on Monday to answer any questions you might have had. You could also feel free to email over the weekend, and I can try to help out as well. And I will see you on Monday.